All right, the next unit that we're going to be doing is working with trig identities. And honestly, this was one of my favorite things in high school because to me it felt like a game. If you could learn all the rules, then you could get really good at it. And it almost doesn't feel like math. It's just a bunch of rules and a bunch of simplifying and trading things and substituting. Some of you guys will love this unit and some of you guys will hate it, but I hope you'd at least give it a shot. So try to think of it as a game and it will be a little bit less painful, hopefully. So first, on your notes, we're going to start off writing the simple trig identities, and you guys know them already. You just haven't worked with them the way that we're going to work with them this unit. So the first trig identity I want you to write down is that sine, oh, that's two I's, sine theta equals 1 over cosecant theta. The opposite of that is true, that cosecant theta is the same as 1 over sine theta. You also know that cos theta is the same as 1 over secant theta. And the opposite would be true. Secant theta is the same as 1 over cos theta. Oops. We also have tan theta is the same as 1 over cotangent theta. And cotangent theta is the same as 1 over tan theta. Hopefully you will also remember that tangent theta, this is, I'm going to stay in red here because we're still talking about these ones. Tangent theta, if you guys remember, is also sine divided by cosine theta. Remember that from when we did the work with the unit circle. And so if I wanted to talk about what cotangent is, I could also take the flipped version of tangent. Sorry, that T ended up looking really weird. Let me fix that. Okay, and so the flipped version of tangent would be cos theta over sine theta. So those are all just straightforward normal trig identities we've already worked with. Those shouldn't really be a surprise. A couple new identities that we're going to look at today are called the Pythagorean identities. One of these days I'm going to make a video where I don't mess anything up. It's going to happen. And to look at these identities, you have to consider what we know about the unit circle. So if you guys remember, we always had x and y coordinates on the unit circle, and the radius of the unit circle is always 1. That's what it meant by unit. So the x coordinate was always cos theta, and the y coordinate was always sine theta. So if I go ahead and build a little right triangle in here, here would be my x coordinate right there. Here's the length of my y coordinate right here. So if I use the Pythagorean theorem, then I know that x squared plus y squared equals 1. But if I want to set that up as a Pythagorean identity using trig, then I can just replace my x with a cos theta, because that's what it really was in the unit circle. And then I can replace my y with a sine theta, because that's really what it was in the unit circle. And then that equals 1. So this is an identity. People don't usually write it that way, though. They actually write this as, and they usually start with sine for some reason, so I'll go ahead and do that. They would write sine squared theta, which is the same as sine theta times sine theta, plus cos squared theta equals 1. So this is the identity. You're also going to see a couple other ways that it's used. People might say that sine squared theta is the same as 1 minus cos squared theta. And they'll also say cos squared theta is the same as 1 minus sine squared theta. So those are all good identities to remember. All right, now in line with that, you can take this identity and you can manipulate it a little bit. So I'm going to rewrite this out, and we're going to manipulate it, and I'm going to show you something. So let's say I wanted to divide through this entire equation, and I'm just going to divide it by cos squared theta. So for my first piece, I would have sine squared theta over cos squared theta. And then cos squared theta over cos squared theta is just 1. And then on the end I'd have 1 over cos squared theta. And hopefully you guys might recognize this, that sine squared theta over cos squared theta is actually tangent. So I could say tan squared theta plus 1 equals, and then hopefully you recognize 1 over cos squared theta is actually secant squared theta. And so this is another Pythagorean identity. So tangent theta squared theta plus 1 equals secant squared theta. Kind of in line with that, you might also see tangent squared theta equals secant squared theta minus 1. That might be something that would show up. So that's another Pythagorean identity right there. And then we're going to do one last one kind of along the same line. If I do sine squared theta plus cos squared theta equals 1, and I divide this whole thing through by sine squared theta, then I'm going to get sine squared theta divided by sine squared theta is 1. Cos squared theta divided by sine squared theta is actually cotangent squared theta. And then 1 over sine squared theta over here is the same as cosecant squared theta. So that's another Pythagorean identity. So you could see it written as that. You might also see cotangent squared theta is the same as cosecant squared theta minus 1. So here's our other Pythagorean identity. So basically what we're going to do is we're going to think of all these different identities as kind of like tools that we have, or like special cards that we have, or whatever in our game, and then we're going to have expressions to simplify, and we're just going to substitute things out until we make it more and more and more simple. So we're going to break things down further and further. So for the rest of this video, just watch. I'm going to do some examples and try to just track with them. And then when we get to class, we'll actually talk about maybe some strategies that will make this game easier for you. And then really it just comes down to practice. The more you do of these, the more you you can kind of see ahead, and you'll see what simplifies because you'll have done it more than once. So this example is going to start off as 1 plus tangent squared, and we're using x's this time. So tangent squared x divided by cosecant squared x. And so I'm just going to look at the top, and I can see that on the top, 1 plus tangent squared x is actually using one of those Pythagorean identities. And so the top of this I could rewrite as secant squared x. So I'm going to take this problem, and I'm going to rewrite the top as secant squared x. But the bottom, I'm not going to change at all. Cosecant squared x. Next, I'm going to go ahead and take secant squared x and write that in terms of cos. So for the top, I'm going to write that as 1 over cos squared x. And then I'm going to go ahead and take the bottom of that fraction and take cosecant squared x and rewrite that as 1 over sine squared x. Now, when we have a fraction over a fraction, if you guys remember, we can do keep it, change it, flip it. So I'm going to keep the first one. I'm going to change that division for the fraction to a multiplication, and I'm going to flip the second one. So sine squared x over 1. Now, when I multiply these two fractions together, you should see that I'm going to have sine squared x on the top, and I'm going to have cos squared x on the bottom. And if you guys recall, sine squared x over cos squared x is actually tangent squared x. So I officially took what I had at the beginning and I condensed it down to just one piece. So tangent squared x is my final answer. And all I did is I took those identities I'd already looked at and I just substituted until I made the problem more simple at the end. All right, next example. Cos x minus cos to the third x. So what cos to the third x is it means that it's cos x times cos x times cos x. There are 3 of them being multiplied together. So I'm going to go ahead and factor this problem. So I can see that both of those pieces have a cos x in common. And when I factor this out, the first one, cos x divided by cos x, means that there's 1 in the first spot. And cos to the third x divided by cos x means that there's a cos squared x left over. Hopefully you'll recognize that this part inside the parentheses is one of those Pythagorean identities. And so what I have inside the parentheses now is actually sine squared x. So I still have cos x in the front of the parentheses, but now inside the parentheses I have sine squared x. And there is no way to condense this down any further, so that's actually my final answer. There's no way to combine those to make them work better. All right, next example. Let's say I have sine x is being multiplied by tan x plus cotangent x. So all I'm going to do is I'm going to take tangent and cotangent and I'm going to rewrite them in terms of sine and cosine. So I still have sine x in the front, but now for tangent x, I'm going to rewrite that as sine x over cos x. And then the cotangent piece I'm going to rewrite as cos x divided by sine x. Next, I'm going to go ahead and distribute that sign inside the problem. And so for my first fraction, I'm now going to have sine squared x on the top because sine times sine makes sine squared. And I have cos x on the bottom. For the second fraction, when I distribute that, I'm going to get sine times cos is sine x times cos x. And there's a sine x on the bottom. Now hopefully what you're seeing here is that the signs will cancel. Sine and sine cancels. So I have sine squared x over cos x plus cos x. Now if I want to make this a fraction where I can combine both pieces of the fraction, then I'm going to need to get a common denominator. So right now the denominator of that fraction is just 1, but if I want to get a common denominator, then I'm going to multiply the top and the bottom by cos of x. So now what this becomes is I have just a huge fraction down here. Cos x is the denominator of the fraction. On the top of the fraction, I have sine squared x from this part. And I have now cosine squared x on this part. And if you guys recognize that sine squared x plus cos squared x is actually that Pythagorean identity, and that just equals 1. This whole top equals 1 now. So now I have 1 over cos x, and 1 over cos x is just secant x. So my final simplification would be that all of this can become secant x.